Welcome, ladies and gentlemen. So let's remind ourselves, right, about the graph of r equals 4 cosine theta. Behind, we can generate this picture quickly, and we'll do it by hand quickly because we've already sketched this last class. So if we were to just choose direction angles theta and then plug them into my formula for r equals 4 cosine theta to generate right points, I could choose some values like 0, pi over 6, pi over 2, 5 pi over 6, and pi. I think we'll get all the way around. Evaluating my r equals 4 cosine theta function, 0, cosine of 0 is 1 times 4 is 4. So I've got in the 0 direction 4. Pi over 6. Cosine is 1/2 times the 4 is the 2, so in the pi over 6 direction, we're going to go 2. Uh-oh. Is that pi over 6? Yeah. Is that 2? Yeah. In the pi over 2 direction, let's see. Cosine of pi over 2 is 0, 0, 0. So in the pi over 2 direction, I'm going 0. 5 pi over 6. Cosine there is negative. Oh, root 3 over 2, that's why. I'm trying to choose pi over 3. That'll be nicer. There we go. Now that gives me 1/2 and 2. Oh, that's much better. Oh, good news. That works. Oh, that's a lot off my mind. I was worried the world was going to crumble over the weekend. 5 pi over, we want 2 pi over 3 then. For doing a nice point. So 2 pi over 3. Sorry. Will give us negative 1/2 times 4 is negative 2. So 2 pi over 3, negative 2. There we go. And pi negative 1, negative 4. Oh, and we're back. Okay. So if we continue making points, we see a nice circle with symmetry, right, about the x-axis, and we saw that was the case with our cosine-based functions in parametric mode. I'm going to put that. Okay, so now let's go ahead and take a look at that in polar mode to remind us how we can use our graphing calculator to produce the same picture. So we've got our polar mode and radians. Okay, and a good starting point, negative 4. Okay, we'll try that, and we'll try that, and we'll enter our 4 cosine theta. And I think I'm going to go around twice now, because I went 0 to 2 pi. Hey, and there we are. And then the challenge question was, let's reproduce this in parametric mode, and that's where we left off last class. So we'll kind of pick up now where we were. We wanted to generate this in parametric mode. Well, the polar graph, right, of r equals f of theta, in this case it was r equals 4 cosine theta, is the curve defined parametrically by, and we can just use our relation between the x and y coordinates in Cartesian mode and our polar graphs. All right, x is given by r cosine theta. And so if r equals f of theta, then x equals whatever that f of theta function is times cosine theta. That gives us our parametric horizontal displacement from the origin. Y is given by not r cosine theta, but r sine theta. And in our BELLWORK, r was that 4 cosine theta. That's my f of theta. So I'll just do that f of theta times sine theta. All right, let's everybody try. So on my graph, on my grapher, I'm going to change my mode to parametric. So I'm in parametric mode now. And so when I go to my y equals, look at, I have an x equals and a y equals equation. No problem. X is given by r times cosine theta. For us, f of theta was 4 cosine theta times another cosine theta. And so when we enter this in our grapher, we're going to get our 4 cosine theta times another cosine theta. But because we're in parametric mode on our grapher, it's using t as the independent variable. Our y is going to be r times sine theta. Our r was 4 cosine theta. So we're going to have 4 cosine theta times sine of theta. Let's see if this works. I'm not sure about my step and everything like that, but I'm going to go. Let's see. We'll keep the 0.1s. Might be good. And let's try it. Oh, how do we do? By golly, you do pretty darn well. Look at those twins. Twinsies. Twinning it. Who knew? Awesome. What questions do you guys have about our BELLWORK today? So the goal here was that we're going to jump off kind of where we were on last class's discussion. Let's continue on. So we've recreated it. Feeling pretty good about it. Wanted to write this here. 4 cosine theta times cosine theta and 4 cosine theta times sine theta. All right, so is everybody in our note sheet? Great. Now I'll go ahead and pause it, and we'll take care of our our first polar assignment from day 3. Okay, ladies and gentlemen. So in our discussion last class, we wanted to determine the slope of a curve that's defined in polar coordinates. So our same old slope, right, dy dx, we've seen in a variety of different contexts. First with our regular y as a function of x, y equals f of x type equations. Then with our implicitly defined relations where we had x's and y's mixed up together on the same side back in AB, right? Then with our parametric equations this year where we had x equals blah, blah, blah with t's in it, and y with blah, blah, blahs and t's in it, and then we had to do dy dt over dx dt to get our slope of the curve dy dx. Well, the same now is going to be applied in the polar arena. Now we'll take the derivative of y with respect to theta over the derivative of x with respect to theta because our y is our sine theta and our x is our cosine theta. Let's see what that looks like. So dy d theta over dx d theta will be our general form for a slope of a polar function. See how that matches nicely with our parametric equations, right? dy dt over dx dt. Cool. So let's go ahead and write an equation to the curve at the point where theta equals 2 pi over 3. And we're going to start with r equals 2 cosine 3 theta. We know from last class that we'll be allowed to use our grapher, right, for the majority of the polar-based problems for the BC test. And so we're going to go ahead and continue working with our grapher today. And so I'm going to go ahead and make sure that my mode now is back to polar mode. And we're going to enter 2 cosine 3 theta. This is one of the families we'll recognize if you've forgotten what this looks like. So I'm going to go back to polar mode, and I'm going to enter r equals 2 cosine 3 theta. That's not good. That's not designed to make me feel good. And I'm going to keep it, 2 pi. We'll see what this does. Did you guys see it? So do you remember from your assignment last class, right, what family of functions this was when you look through the section? Rose curves. Very nice, Danny. So here we've got a rose curve, and we could generate that. It looks like we've got and looks like we have 3 petals in there. Did you guys see that? We have 3 petals. Very nice. Okay, so what do we want to do? We want to write an equation tangent to the curve at the point where theta equals 2 pi over 3. Guess what? The good news is we still need the same 3 things for our equation of the tangent line, don't we? So let's go ahead and see if we can generate the x coordinate of the point of tangency, the y coordinate of the point of tangency, and the slope of the tangent line. Do we think we can do it? I think we can. We can evaluate my my r here and then know that x is given by r cosine theta, and that will generate my my x coordinate in the xy coordinate plane. So let's go ahead and see what r equals when theta equals 2 pi over 3. When theta equals 2 pi over 3, I multiply it by the 3 and I get 2 pi. Is that right? For my angle input? And the cosine of 2 pi is 1. Therefore, r equals 2. We can see this in our 2 pi over 3 direction. There's our 2. Cool. We also know that x is given by r cosine theta. For us, r is 2. So 2 cosine of 2 pi over 3. And the cosine of 2 pi over 3, right, is negative 1/2 times 2 is negative 1. Does that appear to be the x-coordinate of that point? Yes? So we just took the r value that we calculated from our original function, r equals f of theta, and used our Cartesian identity, x equals r cosine theta, to generate the x-coordinate of this point. What did we use for theta? Well, we used our point, right? My theta value at the point of tangency was 2 pi over 3, so I put that in for theta. I used my calculated r value, and I generated negative 1. Graphically, we can see visually that that is, right? That looks like the x-coordinate of the point of tangency. Everybody see that? Cool. How do I get the y-coordinate? Same way. My y-coordinate will be given by r sine of theta. My r value at theta equals 2 pi over 3, we've already calculated to be 2. Therefore, my y-coordinate is given by 2 times the sine of 2 pi over 3. We know that the sine of 2 pi over 3 is root 3 over 2. So I'm getting 2 times root 3 over 2 equals root 3. And we know that's about 1.73. And that looks like a reasonable estimate of that. Okay, so we've got the x-coordinate of the point of tangency, the y-coordinate of the point of tangency, and what are we missing? The slope. How do we get the slope? Good news, we have, right, a formula for the slope of a polar curve. It's dy d theta over dx d theta. Okay, so what was my dy over dx is given by dy d theta over dx d theta, where y is given by r sine theta and x is given by r cosine theta. What's r? R is whatever my polar defined function is. In this case, it's 2 cosine of 3 theta. So what is y? Well, y is given by f of theta times sine of theta. So it's 2 cosine theta, I'm sorry, cosine of 3 theta times sine of theta. Gosh, can we do it? I think we can. I'm going to write this again. So y equals r is 2 cosine 3 theta times, and I still need my sine of theta. What's sine of theta? Sine of theta. And x equals r cosine theta. What's r? R is f of theta, that's 2 cosine 3 theta times cosine theta. Where was the point that I said that the part that I said we could use our graphing calculator for these applications? I remember saying that earlier. Do you guys remember that?
No.
Now. Can we do it now? I think it's worth it evaluating this one time. So let's go ahead and generate dy d theta. What rule would we have to use to generate dy d theta? Yeah, we have, well, yes, and yes. We have to use product and change. So what I'm going to do is I'm going to do this. Oh, almost did the happy dance. All right, so I'm going to do, whoa. Does it seem large to you? No. So dy d theta is the derivative of y, and that's given by a product, right? The derivative of a product of two functions. I'm going to go ahead and do that as first and that as second. What do you guys think? Can we do it? Let's do it. So dy d theta is given by the derivative of the first, right? This is going to go to 2 times cosine differentiates to opposite of sine of input times the derivative of the input. There's the derivative of the first. Times the second. What's the derivative of, I'm sorry, the second straight up is sine theta. Plus the first, 2 cosine 3 theta, times the derivative of the second. Sine differentiates to cosine of theta. Did we get everybody? So the derivative of a product of two functions is the derivative of the first, that would be 2 opposite of sine 3 theta times 3, times the second, plus the first as is, times the derivative of the second. Did we get everybody? Oh my gosh. That's tough stuff. So this is negative 6 sine 3 theta sine theta. Can we write that as sine squared theta? No, these are different angle inputs, so we can't combine them. Grr. Plus 2 cosine 3 theta cosine theta. Hope we don't have to do that again. What's dx theta? I'm thinking we've got a product rule coming again. So dx theta we're given by the derivative of my x equals, this came just from r cosine theta. First function, second function, and the derivative of a product of two functions is the derivative of the first. That's going to differentiate to opposite 6 sine 3 theta, times the second. So is that the derivative of the first? Do I need to do it in parts? We gotta do it once. Times the second, plus the first, times the derivative of the second, and cosine differentiates to opposite sine of theta. I gotta check that first term. I'm not feeling good about it. So let's see, dx theta, the derivative of the first, 2 opposite sine of 3 theta times 3 is negative 6 sine of 3 theta times the second as is plus 1. Everything's okay. Everything's okay. So one more time. That looks like this is negative 6 sine 3 theta cosine theta minus 2 cosine 3 theta sine theta. And Riley, you're in the hot seat. Make sure you don't drop anything. So finally, at long last, dy, sorry, my original slope is given by dy dx equals, what will we write? We'll write dy d theta in simplified form is this bad boy over dx d theta is this in simplified form. Oh, so close to no cigar. Gosh, I was hoping we could reduce something. I don't think we can. You guys see that? Negative 6 sine 3 theta sine theta plus 2 cosine 3 theta. You know it's bad when you can't fit it on your extended page. 2 cosine 3 theta cosine theta. All over negative 6 sine 3 theta cosine theta minus 2 cosine 3 theta sine theta. Okay, what did we want from this dy dx? Back at the original, right, when we started this party, which has since turned into a fiasco. What do we want from this? We just want the slope, so we need to evaluate this at 2 pi over 3. So let's go ahead and get our slope value, and then we can write our equation and change line. And then we can done with this problem. So let's go ahead and try this. 3 times 2 pi over 3 is 2 pi, which means that this whole term, right, is equal to 0 because we get the sine of 2 pi. But this term, right, is going to work out to be 2. The cosine of 2 pi is 1 times the cosine of 2 pi over 3 is negative 1/2. The sine of 3 times 2 pi over 3 is 2 pi is 0, so this term disappears. And this term becomes negative 2 times the cosine of 2 pi over 3 is negative 1/2 times the sine of 2 pi over 3. Nope, that's 3 times, nope, that's 1. Because 3 times 2 pi over 3 is just 2 pi, which is 1. Positive. So the sine of 2 pi over 3 is the only thing we need, and that is root 3 over 2. Is that right? We're going to get this. Very good feeling about this. Negative times positive is negative 1 over negative times positive is negative root 3. So we get root 3 over 3 positive. Moment of truth. Dun 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 dun. I'm going to get a decimal approximation for root 3 over 3. And now I'm going to go to the graph. And I'm going to do second calculate. And check it out. In polar mode, it gives me the option for dy d theta. Did you guys see that? Dy d theta, yes. So I'm going to do it. And what am I going to do it at? I'm going to do it at 2 pi over 3, pinch of salt, and voila! What do we get? No, everybody's good ones. We got the 0.5777, and that's what we wanted because that's what we calculated by hand. So, long story short, we can write our equation of the tangent line in exact form by using my, did I evaluate that? Oh, there it is. There we go. There we go. And what was that? Root 3 over 3 positive. Whew. That was a serious problem. So my equation of the tangent line is y minus root 3, did you just say? Y minus root 3 is equal to, what was my slope? Root 3 over 3. And what was our exponent of point in tangency? Negative 1. So minus negative 1 is plus positive 1. Can we do that? Can we do that? How's that? Awesome. So by wrapping in a tangent line problem instead of just a calculating a slope problem, I'm confident then you'll be able to handle like a lot of different things because we had to do a lot of different things, right, to generate that algebraic by hand. I think that you're going to be able to use your graphing calculator for a lot of the stuff, especially with the area and the volume applications. Okay, so, this was my exercise side of space. Okay, for our final thing, we're going to take a foray into the realm of area. So what I want you to do right now with your partner is go ahead and determine the area of the shaded sector. What's the area of that shaded sector? When we're given the measure of the central angle of the sector and a radius measurement. So take a walk down memory lane and a blast from the past and see if we can generate that.
What did you get? Oh, and where is this?
Seems high.
I think so too. 4.865.
Oh,
Or 16. Well, that's estimated if you want exact. Estimation.
So, and we can use our calculators, but how are you doing it?
Fantastic. How are you doing it?
How are you doing it? So what is it you're doing, Sophia?
How do you find the area of the whole circle and then get the fraction of which the area is.
Got you. So if we did the area of the whole circle, we could use our age-old area formula, pi r squared. Thank you, Sydney. You brighten our room. We can find the area of the whole circle and then take the portion of the circle that we have, namely 70 degrees out of 360 degrees, right? And take that portion and multiply by my whole area to get the area of the sector, the part of the circle that we have. Nice. Thank you, Sophia. So my whole area would be given by pi 5 squared. Yes, or 25 pi. And we want 70 degrees out of the 360 degrees. That's the portion of the circle that we're interested in. So if we take the portion of the circle that we're interested in and multiply it by the area of the entire circle, we'd be left with the area of the portion of the circle. I don't see anything wrong with using the calculator for this bad boy. So I would do 70 out of 360 times 25 pi to get an approximation, and that's about 15.27. Sorry, 272 College Board. Correct, with 3 places. Who had that approximation? Did you guys get that? Great. So the thing is with AP Calculus, we don't work in degrees, right? We typically are working in radians. So let's go ahead and suppose my central angle now is given in radian measure instead. We'll generate the same type of problem, but now in radian mode. What's the area of this sector? So again, we can take our portion of the circle that we have. From last time we saw that was the size of our central angle divided by the total number, right? The total number of radians in the circle. How many radians are in a full circle, by the way? 2 pi. So here's our part of the circle. We have 2 pi over 3 divided by 2 pi times the area of the entire, right? The area of the entire circle would have been our pi r squared, in this case pi 4 squared. Right? So what we're doing is we're generating the generalized form. We take the part of the circle that we have. This was 2 pi over 3 divided by 2 pi is 1/3, so I'm getting 16 pi over 3. Are you guys getting that? And then we can get a decimal approximation for that. It should be a little bit more than 16, like 18. Some 16.755. Like 16.755. Awesome. Okay. So what I wanted to do was use our basic, right, geometric formulas now to generate our method, our strategy for finding area in the polar coordinate plane. So what do we do in each case? Well, in general, the area of a sector with central angle theta and radians in a circle of radius r was given by, what do? Well, we did theta, right, our central angle, out of the number of radians in an entire circle would be 2 pi. That represented the portion, and then times our pi r squared. So for us in general, my area is given by whatever theta, the central angle of my sector is, then what? Well, out of 2 pi times the area of the whole circle would be pi r squared, and we can reduce the sign. So theta out of 2 pi times pi r squared equals what? Well, it equals 1/2 r squared theta. Yes, we can everybody see that? We can divide the pi's out, and that becomes 1/2 r squared, and then times theta, where theta is the measure of my central angle and radians. Yes? Okay. Why? Well, because now we can consider that small differential d theta, the small change in area, as opposed to, right, the area of some sector that's static. And now we're going to go ahead and let the differential dA be given by replacing this theta with d theta. So replacing theta with the differential d theta gives the differential for area dA equals 1/2 r squared d theta, which in turn is exactly what we need to integrate in order to find area and polar coordinates. That is, if d theta is given by 1/2 r squared d theta, then you guessed it, A would be the integral, right? The integral of both sides. We'll be able to find our area exactly by integrating 1/2 r squared d theta, where r is my f of theta. That's my polar curve defined, right, in terms of theta. What? Well, let's try. Let's go ahead and see if we can apply this. So 1/2 r squared is our basic integrator now, right? All right, so the area and polar coordinates. The area of the region between the origin and the curve r equals f of theta for theta in between alpha and beta is given by the integral from alpha lower limit to beta upper limit of 1/2 r squared d theta, where r is f of theta. So typically we'll see this, right? We'll end up plugging in our f of theta function, whatever it is, in for r parentheses squared. So from alpha to beta of 1/2 f of theta squared d theta. And that comes directly from our area of a sector back from geometry. So we generated that from the ground up in the hopes that it would stick. We'll see, right? Sydney.
Like on the AP exam for like a free response, do you have to like look over alpha and beta? Do you have to like do the symbols kind of like that, or is that not too crucial?
No, we'll have to find alpha and beta, as we'll do in just a minute, and figure out, oh, one is pi over 6 and one is 2 pi over 3, and integrate from them. This is just the notation. This is like from A to B.
Like if I wrote A to B though, I don't lose points for the general formula. Like if it wasn't the alpha symbol and beta symbol.
But you're not going to have to write the general formula.
Okay, so.
For it. You're going to have to apply the general formula for a particular curve, if it's a free response thing, as we'll do in just a minute. So let's go ahead and take a look and find the area enclosed in the inner loop of the limazon r equals 1 plus 2 sine theta. What? What does this look like? Huh, let's use our graphing calculator to generate some
Part
type of.
I missed it.
No, I think
Nope.
it was like.
We're saving that until we get to 2. I just did 1 for the printable because then it would fit nicely. Ready? Are we in the right mode? Yes, we are. Do you guys like my little attempt at a French? And you can see I took Spanish, I didn't take French. 1 plus 2 sine theta is a limazon, and I'm going 0 to 2 pi, and it looks like this. Hey, and it looks like that gave us the one full tracing of the curve, right? And we made it all the way around. And we want, oh, and also notice how it's got sine of theta in there, and we've got that vertical axis symmetry, right? Because it was based on the sine function. So we've got that left-right symmetry. All right, now what do we want to do? We want to find the area enclosed in the inner loop. And so where do we want it? Well, we want it just inside here in this inner loop. So how are we going to find that area? Well, we need to determine, right, in between what angles, alpha and beta, right, A and B, C and D, we need to determine what interval of my function traces out that inner loop. And so what can we do? Well, we could watch more carefully, we could guess and check, or we could see that that inner loop appears to begin. Do you guys see that? It appears to begin when the radius, the distance away from my origin, is 0, right? So if I could take this original curve and set it equal to 0, I'd get the those points where I'm 0 units away from the origin, and that would give me a starting point, and I could guess and check with my trace. So let's go ahead and first see if I took this. We won't always set it equal to 0. We're not always going to set this equal to 0. It just happened that this particular one had an inner loop where it looks like the radius started right when it was crossing right there. And so I'm going to go ahead and see if I can't get a guess here for what interval this might be by setting it equal to 0. And that happens when 2 sine theta is equal to -1. And that happens when sine of theta is equal to -1/2. So any guesses for when this loop might start? Well, when's the first time, right, on my rotating in my window that I had my graph for 0 to 2 pi, where the value of sine is -1/2? 7 pi over 6, so I'm guessing 7 pi over 6, right? So let's go ahead and trace 7 pi over 6 and see if that's the case. So here we go. Trace 7 pi over 6. Enter. Oh, by golly, that is when my x and y coordinates are 0. My theta is 7 pi over 6, and watch, as I continue going along, I'm tracing out, look at that. I'm tracing out the inner loop of the limazon, and then until about, well, I'm not sure, except I have an inkling. When's the next place that sine is -1/2? 11 pi over 6, let's check. 11 pi over 6. I want to sit next to Danny when I take the EP. And by golly, there's our 0, 0 again. You guys get that? See what I'm saying? So through inspection, and you're not always going to set r equal to 0, right? It was only the case that graphically I thought that might give us an inkling. Otherwise, right, we could certainly, right, trace and so on and so forth, but we will be able to use our grapher typically to find those values, right, where they're the same. All right, so now what are we going to do? Well, we have our limits. We know that the area in general, right, of a polar curve, that is in between the origin and that polar curve given by r equals f of theta, is the integral from lower limit to upper limit of 1/2 f of theta quantity squared d theta. For us, in particular, this will be given by the integral from where to where? From 7 pi over 6 to 11 pi over 6. Of 1/2 times, and what's my f of theta? Well, f of theta is 1 plus 2 sine theta quantity squared d theta. I've shown the calculus, right? We've determined the limits. We've written it exactly in the integral form. So guess what? Time for Math 9, baby. And I'm going to go to my home screen. And it's just that I'll have thetas in my Math 9 now because we're in polar mode. And so we'll go from 7 pi over 6 to 11 pi over 6. The integral of 1/2 left paren, and I want r was, oh, check it out. I can do vars, y vars, polar r1. Oh, look at that. There's my f of theta squared. I guess I don't need that paren anymore. See if I can mess this up in one fell swoop. I might be able to. We could certainly type that out in parentheses squared, but we need the squared, right, as part of our general formula. I'm going to try that. I typed it out when I was doing it to practice, so we'll see. Hey, that looks familiar. So I'm getting 0.544 corrected 3 places. Were you able to generate on your grapher? Did you type it out or use R? Yeah, you typed it out? Very good. So were you able to generate this? Everybody try it. Make sure you get the same thing. That's pretty sweet. Nice. Okay? Great. Let's take a look at another. let's find the area inside the cardioid, r equals 2 minus 2 cosine theta. Okay, so a cardioid is related to the lemmason. It's just where we don't go in and make that that loop, right? We go in and make kind of like, well, the heart, right? And so let's see what that looks like. We'll clear out our R, and we'll enter our new polar curve, 2 minus 2 cosine theta. How's that? And our graph this time looks like what side is it? All right, so we've got our cardioid, and we want to find the area inside of it. Well, when we did our graph, it looks like we made it 0 to 6.28, so I was 0 to 2 pi, and we traced out the curve exactly once. So it looks like my limits are already given to me. What will my limits be? 1 full circle, 0 to 2 pi. So it looks like 0 to 2 pi are my limits for this one. So we'll go ahead and take our graph, and we can go directly to our area formula. We know that the area in between my polar curve and the origin, right, over an interval alpha to beta, is given by the integral from alpha to beta of 1/2 f of theta quantity squared. The theta in this particular case is given by the integral from 0 to 2 pi of 1/2 f of theta is 2 minus 2 cosine theta squared d theta. And this looks like a job for math 9. So I'll math 9 it up, and I'll go from 0 to 2 pi. Everybody try it, please. And 1/2. And I'll type it this time. 2 minus 2 cosine theta close squared. Riley, check up on it. Perfect. Voila! That's what I got before. Yay! 18.850. 18.850. Awesome. So you guys able to generate that? Okay, so we've got inside a loop, we've got inside a curve. What happens now when we're describing a region, right, that's in between polar curves? And that's the last thing that we need, and that's why we have that blank on another sheet. And so now we need the area between two polar curves. Well, in general, we would do our 1/2 f sub 1 of theta squared, right, minus that inner curve, 1/2 f sub 2 of theta squared, and then all d theta. And so if we have two different curves, call them r sub 1 and r sub 2, we can now take the difference, right, between them. So we'll start with our original one. We know that if we were going to painstakingly write this out, we would have the integral from alpha to beta of 1/2 r1 theta squared minus 1/2 r sub 2 theta squared. And I better do that too. And are we going to write that every time? No. Just like when we were doing our washer method back in AB, right? And we had our pi r squared minus pi r squared, right? We could pull the pi out front and then just do that one, the r squared minus r squared in parentheses, the same thing. We won't use this either. Right? We'll typically see this as our 1/2 integral from alpha to beta, and we will have our r sub 1 theta squared minus typically we'll see that 1/2 as a multiplier in front, and then we'll have quantity r sub 1 theta squared minus r sub 2 of theta, squared. And that's the last thing right back on there for now. So you can scooch back and get that. Can we do it? Can we try it? Can we try it? So now the last questions on your assignment include, right, find the area of the described region, right? And you're going to have to, through inspection, you'll have to guess and check, and you'll have to trace. You're going to have to determine, right, what values in a section here where this happens, and it'll be different for everyone. So let's go ahead and consider the area that's inside the circle r equals 1, but outside the cardioid r equals 1 plus cosine theta. What does this look like? No idea. Let's go ahead and go to our grapher and inspect. We want r sub 1 to be the circle given by r equals 1. I do know what that looks like. And the cardioid given by 1 plus cosine theta. And I might want to change the window here. I like the 0 to 2 pi because I know I'll go once around the circle with that cosine theta, but I don't know that the -4 to 4 and the -3 to -3 is good because my circle is only radius 1, and that'll get me to 2. So maybe I'll try this -3 to 3. Let's see. I don't know if this is going to make much of a difference, but I'm going for it. So there's my, hey! Aww. So we want inside the circle and outside the cardioid. I have no idea. So are you guys seeing where is this region? So it's inside the circle, but it's outside the cardioid. So where are we? We're over on the left-hand side. You guys see that? So we're over here. You guys see that? So in relation to my origin, for this described region, what's going to be my outer curve? Right? What's going to be my outer curve? The red cardioid, oh, that's fitting line style, or the blue circle? What's my outer curve? Which one's further away from the origin? Yeah, the blue circle, that's going to be my outer curve. That'll be my first f of theta quantity squared. Minus the inner curve, then, will be the one that's closer to the origin. And that looks like the cardioid is closer to the origin for this portion of the regions described. You see what I'm saying? Cool. So let's go ahead and figure out this point of intersection. Algebraically, that's when the distance of this curve from the origin is the same where they intersect, right? So algebraically, that would be when r sub 1 equals r sub 2. Are there any places where r sub 1 equals r sub 2? Well, yeah. When does cosine theta equal 0? Pi over 2 and 3 pi over 2. Visually, we see that as straight up as my direction angle theta and straight down as my direction angle theta. But that is through, right? So then I'll go ahead and trace pi over 2 and see. Indeed, even if I up or down arrow and jump back and forth, I'm still at that same point. All right, that -2.05 e to the -10 is 0.0000902, so that's 0. So I'm at the same point, all right? And then if I continue tracing around, there we go. And it should be intersecting the end of the region. That should be at, right, 3 pi over 2. Let's check. 3 pi over 2. So it looks like we have our limits. So it looks like we have our limits. So we'll set up our integral, and we'll go from pi over 2 to 3 pi over 2. I'm wondering, do I want to put my 1/2 out front or out front? Let's go out front. Thanks for asking. And we want r sub 1 of theta quantity squared. So for us, that's going to be 1 squared minus, and now we want r sub 2 of theta quantity squared. So that's going to be parentheses 1 plus cosine of theta, closed quantity squared, closed integrand d theta. Once we've written the calculus once in its entirety, now it's okay to go to math 9. So let's go ahead and go to math 9. and see what we get. So we want, I'm going to do 1/2 out front this time, just to change it up. Let's everybody try, see what happens here. So we want pi over 2 until 3 pi over 2. And we want big quantity, and we want 1 squared. There's still 1. Oh. What did I do? You guys know? I don't know. I blame Riley. I don't know either. Okay. Did it double? That's you, bugger. Okay? Okay? Gosh darn it. Who got 1.215? Oh! That's good news. Gosh darn it. That works. Cool. Beans. Alright guys. I feel like it's been a push, but it's also pretty cool that now look at, we're able to find the area of that irregularly shaped region now in the context of the polar coordinate plane. So that's pretty cool. Alright, so let's close it up. What fundamental identities relate polar and rectangular coordinates? Ooh, we've got lots of chances to call on you for this one. The slope of a polar curve in the xy coordinate plane is given by 3, the area of a region between the origin and the curve r equals f of theta. And then lastly, the final thing that we did, the final new thing that we learned. What about the area of the region between 2 polar curves, call them r sub 1 of theta and r sub 2 of theta. Lots of chances to share. Okay, ladies and gentlemen, go ahead and share our fundamental identities. How is x related to the polar coordinate plane? Danny?
X equals R cosine theta.
Thank you. What's y given by? Tyler?
R sine theta.
Thank you. What plus what equals what? Oh, that's lots of fun. A lot of what's could go in there. Riley?
X squared, y squared, equals r squared.
Very nice. Pythagorean theorem. All right, staying true. And tangent of theta is given what with Cartesian. So what would that look like? Vivian? Y over x, absolutely. Good job. Thank you. The slope of the polar curve in the xy coordinate plane is given by Kobe.
dy d theta over dx.
Good. dy d theta over dx d theta. And then our veritable hodgepodge of notation here. We've got, can we just go right to the integral from alpha to beta of 1/2 f of theta quantity squared d theta. Did I get everybody? You could have also just left this as r, right? 1/2 r squared. That's our general form d theta. Good. And in between 2 curves, and I said r sub 1 of theta. Okay, that's a mouthful. So let's go ahead and do 1/2. You want to pull it out front? Maybe. We'll go for it. And we'll do r sub 1 of theta squared minus r sub 2 of theta squared d theta. Did you get everybody all the pieces? Oh, this is momentous. What do we have to practice from this? To practice from this, we've got 9. Some are slope, right? Some are area of a described region, and some are just area within a curve between the origin. For a whopping total of 9. Then you've got your 2 packets. The OTL out of 9 will be turned in on Monday. The 2 packets will be on our rotating scale, and so again, so when you get an AP packet, right, you got 2 class periods before it's going to be turned in to give you more time to work on it in your schedule. This will be turned in next time, but keep in mind on Monday we'll be taking a timed in-class practice, and so it behooves you to complete this so that you're geared up for Monday. Then you'll get the free response on Monday, and you'll have to complete that so you're geared up for Wednesday. You see what I'm saying?
So you're saying thing.
Awesome. I'll go ahead and save the recording then.